trying to trick you. Component of v onto u. So we're going to be using these formulas but backwards, aren't we? Everywhere we see u, we put v. Everywhere we see v, we put u. Is that all right for me to start with an example like that? Okay, so let's do it. If I want to do the projection of v onto u, the formula should be v dot u over magnitude of u squared times the vector u. So scalar multiple of u. That's basically this formula, switching u and v. Everywhere I see u, I put v. Everywhere I see v, I put u. With me? All right, now we need some things, right? Let's do some scratch work on the side here. What's v dot u? Please be 0? It's not going to. Wouldn't that be nice if it was, though? Wouldn't we be done? So v dot u is going to be, what do we got? -6 plus 28 is 22, right? 22. So we've got one part of it taken care of. That, got it? Okay, the magnitude of u squared. All right, well, the magnitude of u is the square root of the sum of the components squared, right? And then I'm going to square that because I want the magnitude squared. So 4, 16, 20. Is that just 20? I think that's just 20. Okay. Yeah, because it's squared, right? All right, 20. We got the bottom. Good. And then u is just the vector itself. I don't have to do anything with that, right? So I'm going to put 22 over 20, and then the vector 2, 4. Let's reduce that. That's 11/10 times the vector 2, 4. And how do we scale a vector? Just kind of like it's like a distribution. You like just pass the constant through. So this becomes the vector 22 over 10, 44 over 10. Now, I ask you to sketch the results. So I'm going to do that. Somebody, we don't need a calculator for that, right? For this decimal, we can get 2.2, 4.4. Okay, I'm going to try and just sketch this result, just so we understand what we just did, that it matches up visually. These are two-dimensional vectors, so I should be able to draw them. And I'm going to put them both where their tails are at the origin. So I'm going to draw u first. Go out to the right 2. Go up 4. Draw a vector going from here to here. That's my vector u. And then the vector v I'll do in red. That's the vector -3, 7. 4, 5, 6, 7, something like that. Right there. That's v. Sorry about my sloppy little half arrows up there. Okay, which one are we projecting? What? V onto u? Yeah. Do y'all see the perpendicular we dropped down? Where is it? Where does it land? Well, what's our answer? 2.2. I'll do that in purple. I'm doing this to make sure that our answer makes sense, but both visually and practicing doing it, right? So 2.2, go to the right, 2.2 about right there, and go up 4.4, somewhere around there. And it should be parallel, right? So it should be in that same. Does that look like, with my very rough sketch, that would be the orthogonal? Yeah, you know, for a rough sketch. See what we've done? Okay, we move on. Vector projection.
Sir, what is the comp?
Oh, I forgot to do the comp. I'm sorry. What would the comp be? The length of this vector. The length of this vector. I wouldn't even use the formula. I could, but I don't. I mean, I have the vector, don't I? I just need its length. So I would just do the square root of that squared plus that squared. That would give me an answer. I forgot to do it. Thank you for reminding me, Andy. Do y'all want me to do it, or?
Yeah, do you mind?
I don't mind. You need your calculator, though. Will you do it for me? Yeah. Okay, so you're just going to do, for the component, we're doing the component of u, no, v onto u, right? V onto u. So v onto u will be the magnitude of this thing, right? It's the magnitude of that vector that we just got, which is the square root of 2.2 squared plus 4.4 squared. So do all that squaring, then take your square root. You should get approximately 4.91. Sounds good to me. That's the component. So you might be asking, like, why, when would you ever want to use the component versus the projection? You'll see in a minute. This is actually going to be so unbelievably powerful. Let me give you a preview of it, okay? Let me give you a preview, because it'll make it, hopefully make a little more sense as to why we even talk about it. Let's say I have a plane, right? A plane in this room, right? A flat sheet of paper cutting through this room. Not flat on the ground, not a wall, just some angled plane going through here, right? You see it? You see your plane? Okay, now what I'm going to do is I'm going to ask you, what is the shortest distance between the projector and that plane? Do you understand the question? What's the shortest distance? Let's simplify the problem. Let's make the plane the ground, right? If the plane is the ground, what is the shortest distance between that projector and the ground? It would just be a straight line running perpendicular down into the plane, which would just be the z-coordinate of that projector. Yes? Well, that's if the plane is flat, right? If I tilt that plane, the shortest distance is no longer the z. Do you see that? It makes it much more complicated. Yeah? So how would we figure it out? We're going to use a projection. Believe it or not, we're going to use this. So, all right. No, I'm not going to do that one. Okay, that's it for 10.3. See how it goes. Dot product. We're moving on to 10.4. 10.4? 10.4? I remember my dad had a CB in his truck. Good old days. No, he just had, I don't know if he had a handle. He wasn't a truck driver. He just had one just to road trips, talk to people and stuff. Yeah. Fun stuff, man. Okay, so let's take a step back. When we started the section on vectors, we said, hey, if you have vectors, you can scale them, right? You can stretch them, shrink them. You can also flip them over. That was called scalar multiplication. We talked about vector addition, which was parallelogram rule, tail to tip, tip to tail, right? So we learned how to add vectors together, how to subtract them. And then I said, when it comes to multiplication, there are two types, right? Two types of multiplication between vectors. There's the dot product, and then there's a second one, right? We're ready to move to the second one. The unique thing about the dot product was that when we took two vectors and dotted them, we got a number, right? And that was kind of weird. So now we define what's called the cross product. And what do you think we get when we do the cross product of two vectors? We get a vector. Yes, we do, which is good, right? So let me evaluate this whole thing again. Any computer science majors in here? No? No computer science? No computer programming major? No? 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 Wow. Surprise. Okay. All right. So when we have this vectors, we had some notation, right? We said U could be written in its component form, U1, U2. That's two-dimensional. And we could also write that U1 I hat plus U2 J hat. That was that other notation, I hat, J hat. That's two-dimensional. And then three-dimensional, we have the preferred notation, my preferred notation, and then I hat, J hat, K hat. That's for three-dimensional, right? Okay, now, the cross product. There's one drawback to the cross product, and that is it is only defined for vectors in three-dimensional space. So you can only do cross products when your vectors have 3 components. You know, an x component, y component, z component. Which means technically you cannot do a cross product of a vector in 2-dimensional space. There's a workaround though, because anytime you're in 2-dimensional space, you can always step out one more dimension and look at it from the outside and just make your z component 0. I'll show you when we get to an example. So there's a workaround, but I just want to point out that, you know, you have to do a cross product, you have to have vectors in 3 space. All right, so let's take a look at how we're going to do this. If we have 2 vectors, u1, u2, u3, v1, v2, v3, 3 components for each vector, we will now define the cross product. Here's the definition. Memorize it by the end of 30 seconds. Ready? Y'all got that memorized? So we don't ever memorize this. Like, I don't know anyone that memorizes this, okay? Because it's just ugly, all right? This is the formula for it, though. And there's 2 different versions. You can look at them. Okay, I don't want you to even, I just want you to know this exists, all right? What I'm going to do is I'm going to show you how to calculate the cross product using a cute little kind of trick. Not a trick, just a way of doing it. And those of you who've seen cross products, yes? Yeah, cross products? How many of you have seen cross products, have done cross products? So there's like 4 or 5 different cute ways to show people. I'm just going to pick the way that I like. And if you don't like it and you have another way, go for it, that's fine. I'm not going to use that method. I'm going to use a different one. So here we go. So I'm going to show you how to calculate the cross product of 2 vectors using my preferred method. So the way I like to do is this. I'm going to write down first of all I hat, j hat, k hat. Right? I'm going to write I hat, j hat, k hat. Okay, 1, 2, 3. Underneath that, I'm going to write the 2 vectors like rows. Okay, so I'm going to have 2, -3, 5. Those are the components of u. And then I'm going to take 4 and -1 and 3, like that. And notice I did u first, then v, right? U, because I want u cross v. Oh, that's the notation. I didn't say that. The notation for cross product is an actual like old school multiplication symbol. That symbol means cross product. So I first write down ijk, boom, boom, boom. And then I write down the u vector, and then I write down v because I'm doing u cross v. All right. Now what I'm going to do is compute. I'm going to compute the components. Has anyone seen how to do this? Okay, what, off like that picture?
I think so.
Okay, you want to kind of walk me through it?
So I think what you're supposed to do is you replicate a 4th column that has the exact replication of the I hat to the right.
Okay, so you're doing a different one. You're doing one where you do another copy of this over here, something like that. Like
one, not all 3 of those.
Just I?
Yeah, just I.
Okay, so you were using something I'm not going to use. Okay, so that's different. That's okay, and if you're good with that, stick with that. So the way that I like to show it is this. We're going to first figure out, our answer is going to be a vector, okay? Our answer is going to be a vector. It's going to be a 3-dimensional space. I'm just going to put that vector right here. This is going to be our answer. I'm going to go back to the old school notation, all right? And this first component, the way you get that is by covering, we're trying to find the I component, right? The I, this X thing. So what you do is you cover up the I's. You cover up everything in the I column. And you see those 4 numbers? You do the determinant of those. Now what's the determinant? It goes back to matrices, which you may or may not remember or have been shown. So how many of you have seen determinants? What, do you know how to do a determinant of this? Remember? Okay, so determinants are real easy. For when you have 4 numbers like this, the determinant is just this times this. You multiply those, okay, and then you subtract this times this. Okay, I'm going to put this on the side. If you have A, B, C, D, okay, and we want what's called the determinant of this, the determinant, what you do is you do A times D minus C times B. It doesn't matter if I do that multiplications can be reciprocated. So you do this times this minus this times this. All right? That's the determinant. So I am going to do that here. Let me give myself some more room in this vector. This is my answer. Okay, this is my answer. Make it real big, give myself plenty of room. Okay, so I'm going to get my first piece by doing what? I'll write down all the details. Negative 3 times 3 minus, I'm covering up this one. Negative 3 times 3, right? Minus what? So minus negative 1 times 5. Do you all see that the determinant there? That times that minus that times that. That's going to be my first component of my answer. Okay, now I go to the second component. I want to rewrite this because I didn't want to put all that red there. It's just going to get messy that way. Negative 3, 5, 4, negative 1. Okay, so I just want to run through this again. You've got your IJK that just keeps track of things. What's the first, second, and third components? You've got the first vector that you're crossing with the second one. To get the first component, you cover up the first column and you do the determinant on the remaining 4. This times this, minus this times this. Good? Okay, now we move to find the second piece, right? The second component. So I'm going to cover the second component up. And do you see 4 numbers? Yes. You're going to do the determinant on those 4 numbers. All right? But there's a catch. One catch. For the middle one, your answer, we have to change the sign. So just put a negative in front right now in parentheses, and now just do the determinant on those 4 numbers. Just remember, you're going to change the sign on the second one. So I'm going to go 2 times 3. I'm going to write them out in detail. 2 times 3 minus what? 4 times 4 or 4 times 5. Doesn't matter how you do that, right? So it's just the determinant, right? It's the determinant of those 4, but then minus, so subtract, right? Change the sign.
It's accepted?
Accepted, yes. Now, linear algebra, anyone take linear algebra? You do determinants, right, of like 2 by 2, 3 by 3. There's like a general formula for determinants. It's a whole other thing we'd have to get into, why you have alternating sign. So, yeah, just go with it. That's a rabbit hole we don't need to go down right now. Okay, so I had the opposite of the determinant of the remaining 4 numbers, which is here. Okay, now we're moving on to the last component, which is going to be cover this one up, right? And then do the determinant on those 4, and you don't have to change the sign this time. Just keep it whatever it is. So this will be what? 2 times negative 1? Minus, what was it? I'm covering this up. 4 times negative 3. Now I know that this seems like first time you're doing it, it's like, oh my gosh, it's taking forever, it's tedious. You will get a lot more efficient with this. It'll become pretty fast after you do it enough, all right? So what is our first component? Let's see, negative 9 plus 5 minus 4. Okay, all right, this is 6, that looks like a 12. That is 6, take away 20, right? Negative 14, but then minus. So 14? Is that what y'all are getting? When it comes to arithmetic, my brain just says, yeah, no, ask somebody else. I don't even feel like thinking about it. Okay, negative 2 plus 12?
Yeah.
10. There you go. That is the cross product of those 2 vectors. We'll do more cross products. We'll get more practice. Now, a lot of calculators nowadays, like they can do cross products. Some of them, they have an actual cross function on them. And if you have like a TI, graphing one, if it doesn't have cross on it, you can actually program it to do a cross product. Just go Google it. How to program my TI-84 to do cross products. You can teach it. So in this class, you only have a midterm and final in here. There will be some cross products. It's not like they're going to set you back 30 minutes to do a cross product, but I don't mind you using a calculator to do it. I don't mind that. But I won't give you something that requires a cross, like a calculator. At least not on an in-class test. All right, we're moving along, halfway through the class. Okay, now, what the hell is the cross product? Like, what is it, right? It's a vector. We know that the dot product was useful because of that theorem, right? The theorem told us that the dot product, right? If you get 0, the vectors were orthogonal. Yes?
Do we need to write all that out on a test, or can we
What?
just do it on a calculator?
Oh, for a cross product, you just do it. I don't care how you get it.
Okay.
Yeah. The cross product is just it's kind of just a pain in the ass. I mean, we just have to do it, you know. We all have to see how to do it, but at the end of the day, it's just tedious, right? It's like solving a system of linear equations, right? Like a matrix, like 2 by 2 or 3 by 3. It's like, could we do it by hand? Yeah. Do we want to? Do we trust our arithmetic? Do we trust the computer, right? So we turn to the computer a lot to do this, like the heavy lifting of the mechanical stuff, but you should know how to do it. Okay, so what the hell is the cross product, right? We know that it gets a new vector, right? We know we have this new vector. What makes this new vector so special? Well, it's the fact that this new vector is always orthogonal to both the vectors you started with. Okay, now let me explain that visually. Let's say that I have a vector, and pay attention to how I label these. This is u, all right? This is v. They're sitting here in three-dimensional space, u and v. I'm going to cross these two, do the cross product. I'm going to do the cross of u crossed with v. I bring them tail to tail, right? And I do something called the cross product on this. What it does is it generates a new vector, and I'll make it a little longer. This new vector must be orthogonal to this vector and this vector at the same time. So think about this vector u. There are an infinite number of vectors, right, that are orthogonal to it, and there are an infinite number of vectors that are orthogonal to v. But there's only one vector, one non-zero vector, that's orthogonal to both. There's only one. Is it that one? Can't be that, right? It's orthogonal to this one, right? But it's not orthogonal to that one. I have to make it like that, right? Do y'all see that? I'm going to move it to where it's here. Do you see that? You see this red one coming out? You see that if we look at it, let's see, look at it this way. See how it's orthogonal to the one, well, sorry, to this one? And then if I turn it this way, it's orthogonal. Wait, hold on. That way, sorry. Like that. See? It's orthogonal to both. Yes? Yes?
Is it like two planes?
Is what two planes?
I guess like, instead of like thinking of the cross product as a vector, thinking of it as like a line, it would create like two planes of where, so like if we have these two vectors.
These two vectors.
Yeah. Like, the lines that would be orthogonal to it would run across like here all the way throughout that line, and then run across here all the way throughout that line. So it's like.
The reason why I'm thinking about your question a little bit is because this is going to be very much tied into planes and equations of planes and things like that. So I don't want to.
Yeah, I'm thinking about it wrong because it's a vector.
It's a vector, right? So these are not lines because they can move around. Okay.
It could be like up here and it's still orthogonal.
That's right. That's right. It wouldn't happen. So I moved it here, right? But these things, remember, are like, in reality, they can be anywhere, right? So, okay, let's revisit. If you take two vectors, u and v, and you cross them, right, you bring them tail to tail, it'll create a vector that's orthogonal to both. So it creates a vector like this. Or couldn't it have been pointed out the other side? Which way does it point? Well, that depends on the order of the cross product. If you do u crossed v, right, u cross v, then it follows the right-hand rule. Do you remember the right-hand rule for our three-dimensional space? My fingers were down the x-axis. They curled towards the y-axis. the z was positive? If you do u cross v, okay, then u is like the x-axis, v is like the y-axis, and then your thumb is going to be the cross product vector's direction. Make sense? So if I put this here, here's u, here's v. Cross them, y'all tell me. Option 1, option 2. Think 2? 2? 1, 2. So this is u, this is v. I'm going to cross u, cross v. Where should the cross product vector be? Option 1, option 2. It's 2. It is 2. Because you're curling your fingers from u into v, and your thumb is coming out the direction of the cross product. If you do v cross u, it goes the other way around. V cross u, cross product goes this way. All right? All right, so it creates a vector that is orthogonal to both the vectors you started with, which is going to be freaking awesome for what we're going to be doing. All right? We often use cross products. We often use the cross product when we are trying to find a vector that has the property that it is orthogonal to two other vectors. So you might have like a vector and another vector, and you're like, hey, it would be really nice if I could find a vector that's orthogonal to both those vectors. Well, then you say, well, let's just cross those two vectors, and that vector will be orthogonal to both those vectors. All right. So look at this. U is 2, negative 3, 5. V is 4, negative 1, 3. Show that the cross product is orthogonal to u and v. So this is just me verifying what I just said. So didn't we do this problem? We just did the cross product of those two, didn't we? What was our answer? Negative 4, 14. Was it 10?
Yeah.
10. Right, that was what we got when we took u and crossed it with v. Y'all agree? I'm saying here, okay, we found this cross product. I would like for you to now show me what this says, that it is orthogonal to both of those. So how do I do that? I dot it, right? If I take this vector, this new vector, and I dot it with this, I should get what? 0. And if I dot it with this, I should get 0. And then I've shown you that it's orthogonal to both. So let me take u crossed v, and let me dot it with, let's try u first. That will be negative 4, 14, 10. And let's dot that with 2, negative 3, 5. This should work. If it doesn't work, we messed up. Okay, so this should be what? Negative 8 minus 42. And then plus 50, and that is 0. You see me dotting that? Yes?
Is it impossible to get like the cross product for something in 2 dimensions? Because it can't be orthogonal to both.
Well, if I haven't shown you the workaround, but basically what we do is we say if we're in 2-dimensional space, we're just going to act like we're in 2-dimensional space, but we're really going to be in 3. So if you're given a vector like, let's say you're given the vector, to make it easy, 1, 2, and you want to cross that with the vector 3, 4. Then what I would do is I'd say, instead of the vector 1, 2, I'd say the vector 1, 2, 0. And let's cross that with the vector 3, 2, 4, which is exactly how we do torque in physics for 2-dimensional cases. We do something like that, and we say, oh, the torque vector is coming out of the page. It's the same idea. But I'm going to show you torque here at the end. Okay? All right. But in reality, when you have a wrench and you're sitting there tightening a bolt on a car, you're doing 3-dimensional vectors. So your cross product vector is in 3-dimensional space with you. So it's very rare to be in 2-dimensional space in the real world. You know what I mean? Yeah. So it's actually okay that the cross product needs to be in 3D. All right, good. Should we verify the other one? Yeah? I think I'll do it just visually. This dotted with this. So I get negative 16, negative 14. That's negative 30, and then positive 30. So you add them up, you get 0. See? And that's not a coincidence. That is a fundamental property of the cross product of 2 vectors that is always orthogonal to both. Yes?
So with the dot product, we could switch them around. But with the cross product, can we do the same?
You can switch, but what happens? You have to follow that right-hand rule. So if you switch the order of the cross product, what it does is it gives you the same vector pointed in the opposite direction, so it just replaces everything with negative. So if I do v cross u instead, it's going to be 4, negative 14, negative 10.
Okay.
Good question.
So would you always have to prove that it is?
No, this is just to verify. We just, I told you it is, but let me just, try and one example is never enough to convince someone, but at least it's not wrong, right?
Yeah.
It's not, oops, maybe it's not, that's not the property. Okay, so this is just a visual of it, right? If you give me two vectors, the red and the blue, we always get a vector, the black one that's orthogonal to both, okay? This is another picture of the same thing. The reason I have this is because these notes, did I tell you I can get you these interactive notes where you can mess around with stuff? So that's the reason I have this here. Like I told you, when I was in Cal 3, this wasn't here, right? It was just someone up there in front on chalkboard. So having the ability to see the stuff and move it around, which will become extremely useful later because it's going to get much more complicated visuals in here. So yeah, all right. All right, here's an interesting property. If you cross a vector with itself, you get the zero vector. You get the zero vector. You don't get zero, you get the zero vector, right? So let's prove this. Let's say I have a vector u. Let me call that vector u, just for the sake of doing it. Let's call it u1, comma u2, comma u3, right? These are called the components of the vector. Those are my three components of that three-dimensional vector. I want to go ahead and cross that with itself and see if I get the zero vector out. So I'm going to do my cross product. ijk just kind of keeps track of things. I put the vector u1, u2, u3, and then I do it again because I'm crossing it with itself, u1, u2, u3. And now I'm going to do that whole thing where I cover up and then do my little determinants. And I'd have big old vector down here. All right, so to get the first component, I cover this up and do this. What do I get here? u2 times u3 minus u2 times u3. 0. Actually, it may not need all this space. Okay, cover up the middle one, and remember I have to put a negative here, right? Now the determinant. Right? You see what's happening? 0. That's the zero vector. Okay? If you cross a vector with itself, you get the zero vector. What happens if you dot a vector with itself? What do you get? Drum roll. Yes, but what is it? No. That's if you took two orthogonal vectors. I'm saying if you take a vector and dot it with itself, what do you get?
Either double or half itself, right?
You're close.